Let's add a little primer on the greenhouse gas effect as well. Everybody's been exposed to the greenhouse effect at some point, and they are caused by what are called greenhouse gases. And the dominant gases in the atmosphere are, of course, nitrogen and oxygen, but they are symmetric molecules which are not sensitive to the outgoing long wave or the incoming short wave, so they don't do anything. Whereas the asymmetric molecules, like water vapor, carbon dioxide, which looks symmetric but it has a bending mode which makes it sensitive to the outgoing long wave, and others like N2O, ozone, methane, uh, HCFCs, hydrochlorofluorocarbons, and sulfur hexafluoride, and so on, are sensitive to the photons of outgoing long wave. So we said energy is coming from the sun as short wave, and everything is being converted into long wave, and at some time scale the two have to balance, and the balance includes the fact that some of the energy is trapped by the greenhouse gases, reflected or sent back to the surface, which the surface then warms more than just from the short wave, so then it also sends long wave back, which is again absorbed by the atmosphere. But essentially there is a layer of the atmosphere from where the outgoing long wave has to go to space, and as we increase the amount of greenhouse gases in the atmosphere, the amount of energy we are trapping that is trying to go out to space will increase. So there is a net radiative forcing created by increased greenhouse gases from human activities. N2O comes from agricultural activities, methane can come from rice paddies, cattle, coal burning. HCFC, of course, are refrigerants. Sulfur SF6 is used in some electrical manufacturing industries, and so on and so forth. And of course, as we trap more energy and increase the energy coming to the surface as long wave from the atmosphere downward, water vapor in the warmer air also increases, and water vapor is also a greenhouse gas, but it is what is called a feedback gas, because the warmer you make the temperature, more water vapor it can hold if there is water available, like on the ocean. On the desert, of course, you don't have water, so if you warm, you don't get more water vapor necessarily, unless it's being brought in from somewhere by circulation changes. Right. So the water vapor distribution is not very even. If you go to the poles, obviously it's still bone dry because it's so cold. So it's a question of relative change, and it's a feedback gas. So quickly, human beings, of course, have been increasing the CO2. This only goes from the 1979 or so onward, and you can see parts per million here. We have now crossed close to about 418 or 420 parts per million by volume. That sounds like very small. Indeed, it is a trace gas, only about 0.04% of the volume, but it's a strong greenhouse gas and a dominant greenhouse gas, because we are increasing it so rapidly, and it's an inert gas, and it accumulates in the atmosphere because it has a long residence time, which means it doesn't get washed out. So since the Industrial Revolution, or even since the beginning of agriculture, we have been deforesting and emitting CO2, and it's been accumulating, but mostly from the Industrial Revolution on, right? Nitrous oxide, you can see this is now in parts per billion, so that's even smaller, but even that is increasing very, very rapidly. And what matters is the concentration, residence time, and something called global warming potential. If carbon dioxide is considered unit 1 in terms of its ability to trap outgoing long wave, how much higher or lower are the others in trapping greenhouse gases and the energy? That's what is called global warming potential, and we'll see the numbers in a minute. So methane is a more complicated gas. It has shown some trends that are secular, and it's not completely understood. Could be coming from peatlands, wetlands, rice paddies, coal burning, leaks from the abandoned oil wells, and so on and so forth. And CFCs were phased out by the Montreal Protocol, but you can see that they are still not completely gone. This is now in parts per trillion. Okay, there are the various types of HCFCs that replaced the CFCs. Of course, CFCs were replaced because they were harmful to the ozone hole, which was going to affect all life forms. But HCFCs, which were considered a miracle substance to replace HCFC and avoid damaging the ozone hole, ended up being quite bad for greenhouse effect and now global warming, and now we are in a race to replace them, and this is part of the Paris Agreement as well. So take these together. Every change in greenhouse gas ends up producing a net radiative forcing or an imbalance between incoming shortwave and outgoing long wave at the top of the atmosphere, which determines the net temperature balance, thermodynamic balance, energy balance of the planet, right? So we look at it as radiative forcing in watts per meter squared, and you can see CO2 has produced the most so far, close to about 1.8 or so. This is already about 10 years old, so this keeps increasing. Halocarbons, so methane, N2O, and HCFCs are here. Ozone is good when it's in the stratosphere. It protects us from UV, because high energy UV are absorbed by oxygen and ozone. Oxygen is split, ozone is formed, and ozone absorbs the UV, which is good for us. But as a pollutant in the troposphere, it's very bad for health, bad for crop production, as well as it's a greenhouse gas. Okay. Stratospheric water vapor is not good news. As it turns out, global warming is increasing the stratospheric water vapor, which traps the outgoing long wave as well. Black carbon can cool, which is caused by land use and albedo change, whereas black carbon on snow can be harmful because it absorbs shortwave and accelerates the melting of the ice and snow, which means it will reduce the albedo, and hence it's a warming effect, so it's a positive radiative forcing. Aerosols, you can see that these arrows are uncertainties or variances, which are very large for what are called direct effect and cloud albedo effect. So aerosols can directly reflect and scatter sunlight, or they can act as cloud condensation nuclei and so on, and alter the cloud reflectivity, droplet size, rain distribution, and so on. So that's the indirect effect or the cloud albedo effect. And there are contrails from ships and planes, solar irradiance, because solar activity itself is part of the system, sunspots and so on. That is also contributing in the 20th century. And net anthropogenic component of the radiative forcing, then including all these, is standing here at about 1.6 or more now in terms of watts per meter squared. That's what is global warming, right? Just to close this podcast, then let's look at the global warming potential of one molecule of the gas over 100 years. So you have to measure these differences over a certain period of time. It can also be done by weight, but here it's shown by one molecule relative to carbon dioxide, which is considered 1. So each additional molecule of CO2 will produce certain additional warming, and we consider that as unit 1. And then we compare others and also look at average lifetime. So carbon dioxide, as we said, is inert, is well mixed, and it stays for 50 to 200 years or longer. Methane lasts a shorter time, 12 years, highly oxidizable, so converts to carbon monoxide and carbon dioxide, but it has a global warming potential of 21 times CO2. So even though it's a trace amount and it's in parts per billion compared to parts per million of carbon dioxide, it is highly radiative forcing is very high for global warming. Okay, nitrous oxide, 120 years of residence time on average, 310 times CO2 in global warming potential. CFC 12, 11 HFCs lasts for various periods, And you can see this CFC12 has 10,600 times the global warming potential of CO2, and CFC11 is 4,600, and HFC 134A is 1,300 times. Sulfur hexafluoride can last for 3,200 years in the atmosphere, so it's in a small amount, but it's 23,900 times as potent as CO2 in global warming. Not good news, right? So these are the things we have to worry about: concentration, residence time, and global warming potential. Okay, when we put it all together, we are increasing CO2 rather monotonically like this. There are seasonal variabilities which we have taken out. When you look at global warming anomalies with respect to a base period of 1880 to 2019, some base period is usually used, something like 1961 to 1990, and the anomalies are compared with respect to that base period. So we were cooler than the base period. Coming into the Second World War and the end of it, there were some ups and downs, and since then we have basically been warming monotonically, even though there are ups and downs each year, because ocean takes up the heat, evaporation of the ocean takes up energy, excess energy. Ocean takes up 93% of the excess energy created by global warming, and energy can go into melting glaciers. So the temperatures don't increase as monotonically as carbon dioxide, but what we can do is look at global warming patterns and understand why there are higher temperature increases here, and not so much here or here, and so on. So for this course, all you have to remember is that global warming is not uniform. And since this is about health, you want to watch out for regions which are warming rapidly, and whether that translates into changes in weather and seasonality and vegetation and sea level and so on and so forth. Okay. The additional point one could make is that even though the temperature increase is not uniform, if you look at El Niños and La Niñas, which we haven't talked about yet, but I think some of you may have heard about it, I also have podcasts on it that you can look up. But the point is that the warmest and coldest year each decade, you can see that each decade is warmer than the previous decade. Okay, so even though temperature increase is not larger than the previous year every year, each decade is getting warmer than the previous decade. So there is a jump each decade which we have to worry about. Okay. Additionally, we have to worry about how it translates to weather and weather extremes, which is what we will do in the next podcast. Okay. So make sure you understood the basics of the climate in the first podcast and this basic of the global warming. Just for this health purpose, this short introduction should suffice, but you can always go back and find more podcasts, not just mine, but there are lots of them on the internet that you can find. Okay,